In this video, we're going to be talking about exponential functions. Now, let's start out talking about the parent function here. F of x equals ab to the x power. Now, b is the base, and you've got to be careful here because a and b are not both being raised to the x power, just the b. So you have b to the x power and then multiplied by a. b is the base of the function, the base of that exponent. Let's start out by graphing f of x equals 2 to the x, and you can plug in some x values here to find some y. 2 to the 0 power, we know anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the negative 1. Now, to raise something to a negative 1 power, reminder that you need a fraction bar. Bring the 2 to the bottom of the fraction bar. That'll be 1 over 2 to the first power, or 1/2. 2 to the negative 2 will be 1/4. 2 to the negative 3 will be 1/8. And notice you've got an asymptote line there. It kind of levels off. 2 to the negative 4 will be 1/16. 2 to the negative 5 is 1 over 32. Connect our dots, and here's our graph. Now, this graph is an example of exponential growth. Notice it says where a is greater than 0 and b is greater than 1. Now, if it's equal to 1, you got b to the first, 1 to the first, 1 to the second, 1 to the third. It doesn't do anything. But if b is greater than 1, the function is increasing and is called exponential growth. Many things grow exponentially in our real world, such as bacteria. A bacteria growth is an exponential type growth. It's a very quick growth. Notice how we jump from 1 to 2 to 4 to 8, then to 16, 32, 64, very quick growth. Next, let's talk about exponential decay. Let's graph 1/2 to the x power. 1/2 to the first power is 1, or excuse me, 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second is 1/4. 1/2 to the third is 1/8. 1/2 to the negative 2. Remember, if you raise a fraction to a negative exponent, you can flip your fraction. That's the same thing as 2 to the second. So 1/2 to the negative 2 is 1, 2, 3, 4. I skipped negative 1. 1/2 to the negative 1 would be 2. So do you see these two graphs are actually mirror images of each other? And again, notice down here it says where a is greater than 0. So your a is a transformation here. That would flip it if it's negative. If b is between 0 and 1, the function is decreasing from left to right, and notice it's always going downhill until you get to this asymptote line, and it's still going downhill, but it starts leveling off to 0. But this is called exponential decay because it's shrinking. Next up says directions. Classify the functions as exponential growth or decay. We're going to graph it, then we're going to identify its key characteristics. Again, look at your a and b value. Out front, you have a 1 because it's not there. It's understood to be a 1. Since this value here is greater than 1, then this is going to be an exponential growth. Now let's go ahead and graph this. The way we're going to graph it is with a t-table. And you can just plug in a few x values here, maybe negative 2, negative 1, 0, 1, and 2. And here's what you get. And notice it looks a lot like 2 to the x. The only difference is it grows faster. 3 to the first power would be 3, and 3 to the second power 9, instead of the 2 to the first and 2 to the second, which is 1 and 4. The domain here. Notice your graph goes forever left and right. Your domain is all real numbers. Your range, however, you have an asymptote line here at the x-axis. Your range is only from 0 to infinity, and notice the 0 is not included because it is an asymptote line. Your y-intercept is right here. It crosses at 0, 1. You have that horizontal asymptote line at y equals 0. Increasing interval, this function is always increasing. From far left to far right, it's always going uphill, so therefore it has no decreasing interval. Your end behavior. As you travel to the left, or excuse me, to the right on your graph is always increasing. It's going uphill, so therefore your y value approaches infinity. However, as you travel to the left, notice that you level out and your y value approaches 0, that asymptote line. Number 2, 1/3 to the x power. Again, there's nothing out front. So therefore, we're going to go by what's in here. Since this is between 0 and 1, this is going to be an example of exponential decay. Now let's make us a table of values, and it's going to look a lot like our previous graph, and we'll understand why a little bit more in just a little bit. Here's my x values. Let's plug them in. And there is your graph. Notice again, domain is going left and right forever. There's no breaks in that graph. Your range, again, has a horizontal asymptote at y equals 0, so therefore your range is from 0 up, not including that asymptote value. Your y-intercept is the exact same thing because when you plug in 0, it gives you 1. Your increasing interval, there is no increasing on this graph because from left to right, it is always going downhill. And when I say always, that would be from negative infinity to positive infinity. In behavior, as you travel to the right on your graph, notice again your graph levels out to a y value of 0. So as you travel to the right, your y approaches 0. As you travel to the left, your graph increases without bounds, so therefore it would approach infinity. Number 3, 2/5 to the x power. Again, since this base is a fraction between 0 and 1, this would be an example of exponential decay. Let's do a t-table, x and y, and I'm just going to plug in the exact same, and let me zoom in here, plug in the exact same x values of -2, -1, 0, 1, and 2. And a reminder to plug in a -2, all you have to do is flip the fraction and raise it to the +2. So that'd give you a 25/4. To the -1, that'd be 5/2. To the 0 power, that is 1. Anything to the 0, 1. Then you have 2/5 and 4/25. Let's plot those points. And you do see, again, this is an example of exponential decay because we're decreasing. Our domain, there are no breaks. There is nothing you cannot plug in for your x values. Your range is the same, 0 to infinity, because you have that asymptote line at y equals 0. You're never going to raise anything to a power to give you a negative. And that's going to come into play big time when we start talking about logarithms. You cannot raise anything to a power if it's positive to give you a negative. My y-intercept is the exact same, 0, 1, because when I plugged in 0, I got 1. My increasing interval, there is no increasing intervals because from left to right, my function is always going downhill. Now, in behavior, as my graph travels to the right, again, we level out to our asymptote line. My y value would approach 0. As we travel to the left on our graph, it goes uphill to infinity forever. Next problem. We're graphing 4 to the x. Since our base is a positive value greater than 1, this is going to be exponential growth. So now let's go ahead and plug some values in. Create a t-table, and let's see what we get. -2, -1, 0, 1, and 2 should be plenty. And there is my points and graph. We do definitely see exponential growth here. Our domain is the same, negative to positive infinity. Our range is the same, 0 to infinity, because of that asymptote line at y equals 0. Our y-intercept is the same, 0, 1. Increasing interval, this one is always increasing. So therefore, it is never decreasing. And finally, our end behavior. As we travel to the right on our graph, our y value increases to infinity. As we travel to the left, again, we approach that asymptote line. Next up, let's talk about a natural base or of an exponential function. And we're going to start out with the discussion by talking about the number e. E is an irrational number. It's probably the second most famous irrational number. We know that the most famous is probably the number pi, which we all know is 3.14. But the approximate value of e, again, it's a very common number that we use in a lot of our maths, especially when we're dealing with exponential growth or decay. E is an irrational number with an approximate value of 2.71828. ... We know that irrational numbers continue forever. Exponential functions that have the base e are called a natural base exponential function. So that's what we're talking about here. And here is your parent function, y equals e to the x. Many real-world applications, there are many real-world applications of exponential functions. And we'll be talking about those as we progress. And we're going to graph the function y equals e to the x, and we're going to identify its key characteristics. So again, we're going to do a table of value. And there you see the graph, and this looks so much like y equals 3 to the x because, again, 2.718 is nearly 3. So this nearly is the exact same graphs as we've been getting. It will be exponential growth because 2.718 is a number larger than 1. Our domain is all real values. Our range is the same, 0 to infinity, because the asymptote line is y equals 0. Our y-intercept is still 0, 1, because even e raised to the 0 power is equal to 1. It's increasing everywhere, so therefore it's decreasing nowhere. Our end behavior, as x approaches infinity, my y value also goes up and approaches infinity. As x goes to the left or approaches negative infinity, my y value levels out at 0.